Hello. This video will demonstrate how to compute limits. We will look at many examples. We'll also look at the graphs so we can see that our calculation actually does match the visual. At this point, when you're calculating a limit, we've done the first two bullet points. We've looked at a graph and we've used values of x. So for instance, if we're trying to find the limit as we approach x equals 2, we've chosen a number very close to 2 from the left, say 1.999, and we've chosen a number very close to 2 from the right, 2.0001. We've realized if they match, then the limit exists. Now, this is what we're going to do. We're going to look at the limit by analysis. Okay? So for example, the very first one, very simple, but you shouldn't forget it, right? If I have a function, f of x equals 3, we know it's a horizontal line. No matter what x value I'm approaching, from the left or from the right, the limit will always be that constant, in this case, 3. You may want to pause the video at this point for that to make sense to you. But again, choose any value of x you want, come from the right, come from the left, and you'll see that the limit of a constant is actually that constant. Okay. The other really nice one, and this is due to the continuity of a polynomial, and you should know what a polynomial is at this point. Exponents are 0 or greater, and they are integers. We can have no negative exponents, and therefore no variables in a denominator. A polynomial will always be continuous, and therefore finding the limit of a function, finding the limit of a polynomial for any value of x as x approaches any value is simply the value of that function at that value of x. That was a lot of values and x's, all right? Basically, this is saying if you have a polynomial and we want to find the limit of it as x approaches -1, for example, then that simply means we're going to put -1 into our function. Can't always do this, all right? 1 plus 6 is 7, minus 5 is 2. And again, as you can see, as I approach -1 from the left, my limit is 2. As I approach from the right, it is also 2. So this is this one here and this one here are very important and used a lot. These rules, again, you have to commit these to memory. The most important part of this, you can never use these rules unless both limits exist. Okay? And I cannot stress this enough. If we are finding the limit of the sum of two functions, the limit of each function must exist. All right, and let's take a look at that here. If I'm looking at this function, let's ask ourselves, does the limit of x plus 5 as x approaches 0, does it exist? Well, of course it does. It's a polynomial. In fact, that limit is 5. Does the limit of x squared plus 4 exist as we approach 0? Of course, it's a polynomial. It's 4. So, right, if I'm looking at this, I can see that the limit of this function is 5/4, or 1.25, which I can see here. We will see where we will get some problems if the limit of our denominator exists, but it's 0. That cannot happen. So, what happens if the limits don't exist or the limit of the denominator is 0? And this is where you're going to have to remember your algebra, right? You might have to factor or rationalize a numerator or denominator, convert some trig functions if you have cotangent or secant. How do you simplify that to be in the form of sine or cosine? Again, don't forget, in the grand scheme of things, if you forget these, please don't, but if you do, you can always choose a number from the left and from the right and see if the one-side limit exists and see if the one-side limits match. Okay? Let's look at some examples. So here's an example. We want to approach -3. Again, from the graph I can see the limit exists, so you're probably saying, what's the big deal? But we have to be very thoughtful about this if we're going to use our rules, because you may not always have the graph. The limit of the numerator exists. It's 0. The limit of the denominator exists, but it's also 0. So we're going to have to play around with this. And so let's see if we can factor this. All right, I can factor the denominator. And notice what happens. If I can eliminate a factor, we've seen that that means that there is actually a hole in the graph. All right? Again, so it's undefined at x equals -3, but we can see a limit certainly exists. And how will we find out what that limit is without the graph? No problem. What do I have left? Does the limit of 1 exist as I approach -3? Of course, it's 1. Does the limit of x plus 2 exist as I approach -3? Sure, it's -1. And therefore the limit is -1, which I can see here. Okay? You may want to pause this and go through the algebra to make sure it all makes sense. You really need to remember how to factor. In this example, we want to approach 1/2. Okay, and I can see from the denominator the limit exists, but the limit's 0. Okay, so that's a problem. So it doesn't look like I can factor, but the numerator looks, anytime you have a square root or something like this, it's going to clue you in that you might have to rationalize the numerator by using the conjugate. So again, by using the conjugate, I find that I can cancel one of the factors, which again means that the function is undefined at 1/2. All right, but a limit exists. And easy to find that, right? Does the limit of the numerator exist now? Yes, and it's 1. Does the limit of the denominator exist? Yes, and it's not 0, right? 2 times 1/2 is 1. Square root of 1 is 1. 1 plus 1 is 2. So that means that the limit of the original function is 1/2. And again, I can easily see that from the graph. So again, pause this. Make sure these steps make sense to you. While piecewise functions may look a little crazy, they're actually, I think, a little easier to work with. If we're trying to find the limit of this piecewise function as x approaches 2, notice that's the junction where the functions change. So coming from the left, I will be using this function, and I can see that when I substitute 2, of course the limit exists here, right? My limit is 1. Coming from the right, I'm going to use this function. Well, what's 1/2 of 2? 1. So the limit from the right exists, and it's 1. The limit from the left exists, and it is also 1. Therefore, the limit of the piecewise function is 1. Okay? Looking at this function, I can see as I approach -2, the denominator is going to be 0, so this function does not exist at -2. So, it doesn't look like I'm going to rationalize the denominator. There's no trig, so maybe there's going to be some factoring involved. So as you can see, I can factor the denominator here. I need to get a common denominator. I simplify. I see that I can cancel a factor of x plus 2, which means the function is undefined at -2, but from the graph I can see a limit exists. There's a hole here, all right? So now the limit simply becomes the limit as I approach -2 of 1 over x minus 2, which is 1 over, okay, does the limit of 1 exist as I approach -2? Yes. Does the limit of this exist? Yes. So the limit turns out to be -1/4 or -0.25, and I hope that you can see that that matches here on the graph. Okay, here's another example. I'm approaching 1 for this function. You can see that the function, the limit exists for the numerator, it's 0. The limit of the denominator exists, but it's 0. So what can we do? As I've mentioned, you really have to know your algebra because you have to know how to factor the difference of cubes, which in this case is this. I can see that I can cancel a factor. There's a hole at x equals 1, so it's undefined, but we can see a limit exists. What I'm left with is a polynomial. As x approaches 1, I simply find the value of this function at 1, which is 3, and it matches. Right, I'm not going to spend a lot of time on this one. This is a really neat theorem and very simple to see. Right? Because the graph is continuous at x equals 2, I can simply find the limit of, sorry about that. Just put 2 in here. That's going to give us the square root of 3. All right. If I find the limit of this, that's 3. And I'm taking the square root of that. All right, so the limit of a root as we approach some number is the same as the root of the limit. No problem. And even more limits to remember. Okay, really commit these to memory. These 3 in purple, really pay attention to. These are very useful. These are also useful because these limits do not exist. Okay? Really understand the difference between them. Use a graphing program so you can actually see this as well. Okay? And don't forget these. These are fun. So here's an example where I don't know anything about secant of x. Okay? But I do know that secant of x is 1 over cosine, correct? All right, and this is where I've said in class it's kind of like a puzzle. You have to think about, okay, how is this going to help me? So you might want to break this up and do something like that. Okay, so now I can see, does the limit of x exist as I approach 0? Yes, it's 0. Does the limit of x over cosine of x exist? And you're saying, how do I know that? Well, you should remember that from here. Okay, yes, it exists and it is 0. Okay, and therefore the limit of this is 0. Again, I can see that on my graph, no problem, but you have to be able to do this without looking at the graph. And this part here, going from x squared to x times x, really we got to be thoughtful about that. So you may want to pause and look at this a little more carefully. Okay, so let's look at this one here, right? The inverse cosine of x squared. And you're saying, oh, geez, I don't know what that is, right? But x, as we're looking at, as x approaches 0. So don't forget this piece, right here, all right? This is defined from -1 to +1, and obviously since 0 is included in that, that's nice and easy. The inverse cosine of 0 squared, right, if you remember cosine, right, is pi over 2, correct? All right, and pi over 2, if you think about that, is going to be 1.57 is what we can see here. Okay, one more. And the last one, x raised to the x squared. We don't know what to do with this, so we're going to choose a number very, very close to 0 from the right. and we can see that it's 1. Well, I hope this helps. Thanks for watching.